Welcome back to our review of option A. We saw last time that when a car produces a sound, the car is the source in this case, that sound will be perceived as a different frequency by an observer if the car is moving. So here's a moving source and a stationary observer. For the person here, the observer, the car is approaching and the wavefronts are compressed. They're squished together. So this person hears a lower frequency. If the car, the source of the sound, is receding away from another observer, then that observer hears a lower frequency because these wavefronts are spread out. The same Doppler shift can be produced even when the car is at rest. So now the car, which is the source of sound, is not moving, but the observer is. The observer here hears a higher frequency because she is intercepting more wavefronts per second. As she strikes one wave, she then moves into the next wave, decreasing the time it takes to receive the second wavefront. So a higher frequency is heard. Here's the equation we learned for the Doppler shift when dealing with sound. C is the speed of sound waves. This is the speed of the observer. This is the speed of the source, which makes the sound. This is the original unshifted frequency, which is emitted. This is the shifted frequency, which is observed. We use positive values whenever there is approach, negative values whenever there is recession. Here's the equation that we use when we're calculating the Doppler shift for light. Delta F is the amount of change in the frequency. F prime is the received shifted frequency that the person sees. V is the speed of the thing that's moving. It's the relative speed between the objects. And C is the speed of the light waves. Now, in this equation, a brief note. In the data booklet, this value is misprinted as F. You look at that F and you remember, for light, it's actually F prime. We can use the Doppler shift to measure how fast blood cells are moving. Here's the equation. There's a 2 added into the equation because there are 2 Doppler shifts. The first occurs when the cell receives the ultrasound beam. In that case, the cell acts as a moving observer. And then the cell reflects a beam and acts as a moving source. So there are 2 shifts. One when the cell is a moving observer, a second when the cell is a moving source, and these 2 shifts add together or superpose. The reason there's a cosine theta in the equation is because we need the velocity component, which is parallel to the ultrasound beam. That parallel component is the only thing responsible for making a Doppler shift at all. So cosine theta, that factor, gives us the parallel component. We learned about diffraction. There are 3 things that can happen when waves strike a slit. If the slit is really, really tiny compared to the wavelength, really small slit, see how small? When the waves come and strike, they spread out, and it's as though we drop a rock into the water. There's a single point source, we could say, and circular waves spread from the point source. When the slit is a little bigger, roughly equal to the wavelength, it's as though there's not just one point source, but multiple point sources, one here, one here. Those 2 point sources interfere because they produce waves that lie on top of each other. There's constructive interference, destructive, and when those waves hit the back screen, we see a pattern of bright and dark spots. When there's a really huge slit length, B, the waves come in and they do this. The example we studied is the one in the middle. So here it is again. We have some laser. It's producing some light, so we call it a source of light. We send that light through a slit with length B, or width B. When the laser light, or when the light passes through the slit, it diffracts, and what we get on the back wall is this pattern of bright spots and dark spots. There's one big bright spot in the middle called the central maximum. We can plot how bright the light is with an intensity graph. Really bright means the graph is high. So we flip the graph on its side so that we put it on top of the screen. Right here, I've just drawn a dotted line to the first dark spot where intensity goes to 0, drops to 0, so no light there. We can mark that angle, theta, of the first intensity minimum, and let's mark it on the other side. This distance we call d, and we can mark it on both sides. A much larger distance is from the from the slit to the screen. We call that big D. Here's the equations. These are the equations we can use, which apply to diffraction. And the central maximum, that big bright spot, remember, here it is again, is equal to 2D. We normally put the graph like this on its normal, so we put it the right way, in the right orientation, the correct orientation. And we can mark the angle where the intensity drops to 0. That's the first dark spot, which we've marked theta minimum in our diagram. Resolution occurs when we're trying to resolve two objects. So maybe there's two lasers producing light. Each laser is passing through a slit with width b. The first laser sends its light through and diffracts upon passing through the slit. The diffraction pattern is centered on the spot where this beam hits the screen. So there it is. I've centered the diffraction pattern on that spot. The second light source sends light through. It diffracts when it passes through the slit, and it has a diffraction pattern formed, which is centered on the spot where this ray strikes the screen. This angle between the two is the angle, the minimum angle, where the two sources can still be resolved or seen as distinct. Now, we notice that these two sources are seen as distinct when the central max of one diffraction pattern, here it is, the central max of one diffraction pattern, overlaps with or lies on the first minimum of the other. If the two patterns are any closer, we can't resolve the two sources as distinct objects. They look like just one blurry object. We can mark this distance little d. The much larger distance is from the slit to the screen. And here are the equations that we can use to solve problems. This equation is called the Rayleigh Criterion, but if you were ever asked to write what the Rayleigh Criterion is, or describe it or state it, you would want to talk about the shapes of the diffraction patterns, not the equation. So here's that shape again. The first central max of one pattern overlaps with the first minimum of the other. And from one maximum to the other is from here to here. That's theta, where they are just resolved. This should say resolved. We learned about polarized light. Polarized light is light where the electric field vector always oscillates in the same plane. And that plane of oscillation is perpendicular to where the light is going. For example, if we have horizontally polarized light, then the electric field oscillations are all in the horizontal plane. That plane is perpendicular to the direction of energy propagation. So there's the forward arrow shows where the wave is going. Here's how we draw a vertically polarized light, and we've shown that plane of polarization, or we also call it the plane of electric field oscillation. Unpolarized light is light in which the electric field vector, or the plane of its vibration, is always and randomly changing directions. First it's up, then it switches again, and so every possible direction is represented. The electric field vector oscillates or changes randomly between every direction. We can represent this using vertically and horizontally polarized light on top of each other, added together. So we can imagine unpolarized light. We can imagine it this way. Polarizing filters are an example of polarization by transmission. We send light through the filter, and the light becomes polarized. This filter is just a device made of a special material which only transmits one component of the electric field vector. And this is how we can show it. If we take this Polaroid or polarizing filter and we rotate it, no matter what angle we move this to, we will always only have half of the unpolarized light passing through. So if the initial intensity is this, the amount that gets through the Polaroid is always half when the incident light is unpolarized. On the other hand, if the incident light is polarized, so now we have vertically polarized incident light. When it strikes this filter, if the filter is vertical, all of it gets through. I represents how much is transmitted through the filter. So we could mark a point. When the angle is 0, we have this point. If we take this, this filter and we rotate it slightly to an angle, then now less light gets through. And the equation for Malice's law tells us how much light will get through. So we could mark a point showing that less light is through when we rotate our initially vertical filter. If we rotate the filter even farther so that it is at 90 degrees, then now no light will get through because the cosine squared of 90 is 0. And so if we plot all these points, the graph does this. It makes a cosine squared shape. And eventually, we get back up to the full intensity once we've rotated this thing 180 degrees, because it'll look like the far left again. If we have the same picture, right, a vertically oriented filter, but we start out with horizontally polarized light instead of vertically polarized light, then the shape is like this. We learned about Brewster's angle, which is polarization by reflection. If you send light toward a water surface which is horizontal, some light is reflected off, some is sent into the water and refracts. We mark the normal line and we measure the angles of incidence and reflection from normal. This is the angle of refraction. When the reflected ray and the refracted ray are at right angles, something special happens. All of the light which is reflected is horizontally polarized, and all of the refracted light is vertically polarized. That angle is called Brewster's angle, and it's equal, of course, the angle of incidence is equal to the angle of reflection. We could use some geometry to prove that this is 90 minus Brewster's angle. We know that air has a refractive index of 1, and we'll just call the refractive index of water just n. If we take the ratio of n over 1, the ratio of refractive indices, we could use Snell's law to say that this is sine of Brewster's angle times sine of 90 minus Brewster's angle. On the left side, we have just n. But on the bottom, sine of 90 minus phi, that's equal to cosine of phi. And of course, sine over cosine of an angle is equal to tangent of the angle. When we solve for Brewster's angle, we get this equation. This is Brewster's law.